In this video, we're going to talk about how to solve a system of equations. And a system of equations is just putting together two or more equations that you want to solve. So that means that typically when we solve an equation, you're looking for the value of the variables that make the equation true. So in a system of equations, you're looking for the value of the variables that makes all the equations in the system true. So I want to show you real quick a graphical representation of what a linear system would look like. So this is a linear system with two equations in the system. So in that first drawing, you can see what would happen if I graphed two lines on the same XY coordinate plane. And there are three things that can happen. And the first one there shows the two lines intersecting at one point. So that one point where they intersect is the solution to the system. So graphically, I can see where that solution is. And when I have one unique solution to the system, it's called a consistent system. Now, moving to the second drawing, I have a graph of two parallel lines. So if the intersection is the solution to the system, if I have two parallel lines, meaning they never intersect, then that means that this is a system with no solution, and that's known as an inconsistent system. And finally, the third thing that can happen is that the two equations may not necessarily look alike when you look at their equations, but when you actually graph them, they are the exact same set of points. They actually describe the exact same line. So that means that every single point would be a point that they share in common. And that's known as a dependent system, and it's going to have infinitely many solutions since there are infinitely many points that those two lines share in common. Now, graphing isn't the best way to solve a system of equations because even in this first case here where I've got one unique solution, identifying the value of that ordered pair isn't always easy. Now it is if they happen to intersect at a nice point like -1, 2, but what if they intersect, what if this intersection point here was -11/18, 15/8? Now that would be very hard to see on a graph. So we need an algebraic way to come up with what that exact solution might be. So there are two algebraic methods that we're going to talk about. And the first one is called the substitution method. And it does what it sounds like. We're actually going to substitute one of the equations into the other. So what I first have to do is identify one variable from one equation and get that variable alone on one side. And to do that, what I want to do is pick a variable that has a coefficient of 1, because then I don't have to divide, which means that what I'm substituting isn't necessarily going to contain an algebraic fraction. So remember too that when you're solving, you're looking for a point where these two lines intersect. So that means my answer should be an ordered pair. So don't forget to find both x and y. So let's look at that first example. So the first thing I want is to identify a variable in one of those equations that has a coefficient of 1. So this x right here has a coefficient of 1. So that's the variable that I'm going to start with, and I'm going to get that variable alone on one side. So to do that, I just need to subtract that 2y from both sides. So that changes this equation into x equals 5 minus 2y. And now's where the substitution comes in. So what I'm going to do is substitute what this x is equal to. So that algebraic expression is going to get substituted into the x in the other equation. So let's rewrite what that's going to look like then. So I have the 3 times x, but in place of the x, I'm going to put that algebraic expression 5 minus 2y. And you want to make sure you've got parentheses around that. And then I'm just going to finish the rest of the equation. So the rest of the equation is minus y equals 15. So now notice I've changed this system from 2 equations with 2 variables into a single equation with 1 variable. And so I can solve now for that variable. So this is just a linear equation, so we just want to clear those parentheses out. So I'm going to distribute that 3 through the parentheses. And then I'm going to combine my like terms on the left. So that's going to give me negative 7y. And I'm also going to move this 15 to the other side. So I'm going to subtract that 15. And I get negative 7y equals 0. So dividing both sides by negative 7, I get y is equal to 0. Now, just don't get all excited and circle that and then move along, because remember, we want to make sure that we find a complete ordered pair. So this is half of that ordered pair. So our answer is going to be an x comma y. So we have the y part, but we need to figure out what the x part is. So to do that, we're actually going to use this new equation we came up with up here where we solve for x. And we're just going to substitute what we got for y into that. So that means that we're going to have x is equal to 5 minus 2. And in place of that y, we're going to substitute our 0. And then we're just going to do the arithmetic on that right-hand side. So x is going to equal to 5 minus 0, or 5. So now we have the rest of that ordered pair. So there's the solution to the system. So I know that if I graph these lines, these 2 lines would intersect at that point 5, 0. Okay, let's take a look at a second example. Now, in this example, notice that y is already alone, and it's already alone in both equations. So I'm ready right now to just go straight to the substitution. I don't need to get a variable alone on one side. So that means that I'm going to go ahead and substitute what this y is equal to. That algebraic expression is going to go in for the y in that second equation. So I'm going to set negative 2x plus 3 is going to be equal to 3x plus 5. Now I've got a single equation that only has 1 variable, so I can solve for that variable. So I need my x's on one side, my constants on the other. So I'm going to go ahead and add 2x to both sides to get my x's over there on the right. And that's going to leave me 3 equals 5x plus 5. And now to solve that, I just need to subtract the 5 and then divide by 5. So subtracting the 5 gives me negative 2. And dividing by 5 gives me negative 2/5 is equal to x. So again, we're looking for an ordered pair for our answer. And we've got the first half of that ordered pair, but we need the second half. And I know it's not great that this is a fraction, but sometimes we're going to get fractions, so you just got to deal with it. All right, so we're going to plug this negative 2/5 in for x, and we can go back to either one of those original equations because both of those equations are solved for y. So you can pick either one. Generally, I just usually pick the first one that's there in the system. So I'm going to use this first equation, and I'm going to replace that x with my negative 2/5. So that's going to give me y equals negative 2 times negative 2/5 plus 3. And so I just need to do that arithmetic. So you can get on your calculator and do it if you want. If we do it by hand here, when I multiply negative 2 times negative 2/5, I get positive 4/5 plus 3. And if I change that 3 into a common denominator of 5, I'm going to have 4/5 plus 15/5, which gives me a y value of 19/5. So I have the other half of that ordered pair, and there's the solution to my system. Okay, now I mentioned there were two algebraic methods. Now, substitution method is not my favorite method. In fact, whenever I have to solve a system of equations, it's this second algebraic method that I always choose to use. And the reason for that is because in that substitution method, remember, I needed to start off by getting a variable by itself, and I want a coefficient of 1 when I do that. Well, most of the time, you're not going to have a variable that has a coefficient of 1. So that substitution method doesn't always work as the best method. So for me, if I've got one method that will always work, then that tends to be the method that I'm going to go for. So I'm going to use this elimination method typically anytime I'm solving a system. Okay, so this is called the elimination or addition method, and the addition method describes what we're going to do. We're literally going to add these two equations together in a way that one of the variables gets eliminated, and that'll allow us to solve for the other variable, and then we can substitute that back in to find the second one. Now, there might be a little bit of manipulation that you have to do first before you can add them together. And what I mean by that is if you look at this first example, if I went ahead and added these together right now, I'd get 3x plus y equals 0. And that doesn't get me anywhere because, yeah, I have a single equation, but I have a single equation that has two variables. And I can't solve for either one of those variables when that happens. So what I want to be able to do is add these together where one of those variables drops out of the equation. So to do that, think about what would make that happen. Take, for example, let's say that I had 4x added to negative 4x. That would drop out that x term. Or if I had negative 3y added to a 3y, that would drop the y term out. So what I need in order for a variable to drop out of the system is their coefficients have to be opposites of each other. So same number, one of them positive, one of them negative. So that's the manipulation that I'm talking about that we have to come up with before we actually add the two equations together. Okay, so let me get rid of this. And then what we're going to do is look at what we can do to get opposite coefficients on one of the variables. So when I'm looking at my variables, the first thing I want to do is choose which variable I'm going to eliminate. So when I look at these variables, when I look at the x's, for example, I've got a coefficient of 1 and a coefficient of 2. So if I'm going to choose to eliminate the x's, what I need are those coefficients to be common multiples of each other. So the coefficient of x right now is a 1 and a positive 2, and the least common multiple for a 1 and 2 is 2. So all I need to do to get these equations set up is to multiply this top equation by 2, and that will give me the same coefficient of x. And now remember, I need opposites, so I'm just going to throw a negative in front of that 2, and that'll give me the coefficient I need on the x for the x's to eliminate. Now remember, when you multiply by negative 2, you need to multiply the entire equation by negative 2, not just the x, because you want to keep the line equivalent. So let's go ahead and do that. So if I multiply that top equation by negative 2, I'm going to have negative 2x minus 4y equals positive 10. Now, the bottom equation is remaining exactly the same. And now you can see that when I add these two equations together, I'm going to get an equation where the x's drop out, because negative 2x plus 2x is 0, so the x's are gone from the equation. And then when I add my y's together, I get negative 5y equals 15 on the constant side. And I have an equation with one variable that I can solve for. So to solve for y, I just need to divide both sides by negative 5, and there's my y value. So I have half of that ordered pair solution. Now to get the x, I'm going to need to substitute that y back into either one of these original equations. It doesn't matter which one you plug it into. You'll get the same x value back either way. So I'm just going to pick the first equation, x plus 2, and in place of the y, I'm going to substitute in my negative 3, and then multiply those two constants together. Oops, that's a plus sign. And add the 6. And there's my x value. So the ordered pair where these two lines intersect is at 1, negative 3. Okay, let's take a look at one more. On number 4, when I'm looking at which variable I want to eliminate, let's take a look at the coefficients of each. So when I look at the coefficients of x, I've got a 3 and a negative 7. So the least common multiple for 3 and negative 7, or 3 and 7, would be 21. And when I look at my y's, the least common multiple for 2 and 3 is 6. So in this case, both equations are going to have to change in order to eliminate one of those variables. So when both of them have to change, it really does not matter which variable you choose to eliminate. So I might choose to eliminate the y's in this one just because the least common multiple is a smaller number. So the smaller the numbers, the easier the arithmetic is. So I'm going to do that on this one, eliminate the y values, but if you want to try it eliminating the x's, that's fine. We should still get the same answer. Okay, so if I'm going to choose to eliminate my y's, let's think about what we need to multiply by in order to get 6's in front of those y's. So that's going to mean that I need to multiply this first equation by 3, because the 3 times the negative 2 would give me the 6 that I need. And then I'd have to multiply the second equation by 2, since the 2 times the 3 would give me the 6 that I need. Now, I don't need either one of those to be negative because I've already got opposite signs in front of the y's already. Okay, so the first equation gets multiplied by 3. That gives me 9x minus 6y equals 3. The second equation gets multiplied by 2, so that's negative 14x plus 6y equals 2. And then I'll go ahead and add those together, and the y's should drop out. So 9 plus negative 14 is negative 5x. And notice the y's are going to subtract out, equals 5. And now I've got a single equation that I can solve for x. So I get x is equal to negative 1. So there's half of my ordered pair. And now I want to substitute that negative 1 back into either one of those first equations. Does not matter which one. So I'm just going to choose the first equation for no particular reason. So the first equation is 3 times x, and in place of the x, I put in my negative 1. And I'm going to move this negative 3 to the other side by adding 3. Divide by negative 2, and there's the second half of my ordered pair. So the solution to that system is negative 1, negative 2. Okay, now in every example that I showed, the two substitutions and these two, we had consistent systems. So in this case, we had a unique answer to all four of these examples. So I do want to show you one more quick example of a system that's not consistent. So we get either infinite solutions or no solution. So this one is a little bit different than the other ones. Now, how we start off is the same. I'm going to look at my least common multiples for each one of these. So for my x's, my least common multiple is 6. For my y values, my least common multiple would be 18. So I'm going to choose to eliminate the x's just because it's a smaller least common multiple. So that means multiplying the top equation by 3 and the second equation by 2. And this time I am going to have to throw in a negative on one of those because I need the signs to be opposite. So if I multiply that top equation by -3, I'm going to get -6x minus 18y equals -21. And if I multiply the bottom equation by 2, I get 6x plus 18y equals 20. So go ahead and add them together. And when I go and add the x's together, they do eliminate like I wanted them to. But look at what happens with the y's. When I go to add the y's together, they're also going to get eliminated. So when both variables get eliminated, that's telling you that this is either a no solution or an infinite solution. Now, the way that you tell is to go ahead and finish the adding. So when I add this left-hand side together, since everything eliminates, my left-hand side is 0. Now, when I add the right-hand side together, -21 plus 20, I get -1. So it's this statement that tells you whether it's infinite solution or no solution. And when you look at this statement right here, this is a false statement. 0 does not equal -1. And when that statement is false, that's telling you that this system has no solution. So these are two parallel lines. In the case of infinite solution, what you would end up with is 0 equaling 0. So if you get a true statement, then that's a system where the two lines were the same, and you would just state that the system has infinite solutions. Okay, so this was our last section of the semester. So take a look at this homework, and if you have any questions on the video or the homework, make sure you email me. And once you're done with this homework, start studying for your final exam.